this video, we'll see how to use actuarial method for estimating survival function of the population. As seen in the earlier video, actuarial method is a non-parametric method to estimate survival function of the population. So here the population distribution will be unknown, and based on the sample, we will be estimating population survival function. So as for example, suppose there were 200 engine aircraft at the start of the experiment, that is at the start of the year 1981. Then during the year 1981, 5 of the engines got failed. During the year 1982, 10 engines got failed. Similarly, for the year 1990, 3 engines got failed. Apart from the failure, there may be some other reasons because of which engines might have been removed from the system. So therefore, we are considering number of removals also. So year-wise, removals of the engine, that count has been provided. So during the year 1981, no engine was removed. During the year 1984, 2 engines were removed. Now note that these 2 engines were not removed because of failure. Their removal reason must be something different than the failure. Because if it got failed, then it will appear in the second column, number of failures. So number of removals is because of the reason that will be something different than the failure. So once this data is provided, we can use this data to have estimate of population survival function. So suppose we consider this data in some scaled time axis. So for the year 1981, at the start of 1981, we will fix origin as 0. So starting from 0, at the end of year 1990, we will have count as 10. So this entire period of 1st January 1981 to 31st December 1990, that can be considered as the time range like 0 to 10. And this range is divided year by 0 to 1, 1 to 2, 9 to 10. So for this particular data, we are going to have estimates of survival function at the nodal points. That means we will have estimate of survival function at time point 1. We will have estimate at time point 2. Similarly, we will have estimates at time point 3, 4 and so on up to 10. So for this particular setup, we will be considering these particular things. That is, at the start of the interval 0 to 1, how many engines were working at the start of that particular interval. Similarly, how many failures were there in that particular interval 0 to 1, that will be denoted by DI. So DI is the number of components failed during the interval. Similarly, apart from failure, if some engines have been removed from the system because of some other reason, then those will be censored. So censored during the interval, that will be nothing but addition of Li plus Wi. Li is nothing but loss to follow, Wi is withdrawal with our standard terminology. Here in this case, number of removals will stand for Li plus Wi, because whatever be the reason, their collection total count is given as number of removals. We don't have splitted count as Li and Wi. So this particular data can be considered here. So during the time interval 0 to 1, 5 components, 5 engines were failed, 0 number of engines were removed from the system. That is, there is 0 censoring in the interval 0 to 1. In the interval 1 to 2, 10 failures are there and 1 removal from the system. That is, 1 censoring has been occurred. So if we consider this data, the number of components that were available at the start of first interval were 200. It is provided that there were 200 engine aircraft at the start of the system, at the start of the year 1981. So out of these 200, these 5 got failed during that particular year and 0 were censored. So 200 minus these many engines will appear here. That is, if we start with 200 engines at time point 0 and during the time interval 0 to 1, if some number of engines have got failed and some have got censored, those many engines have to be subtracted. Those many number of that many number of engines have to be subtracted from this particular 200. So here the number that is going to appear will be this 200 minus, it will be addition of held component plus addition of censored component. So out of 200, 5 got held, 0 got censored. So at the start of second interval, we will have 195 working engines at the start of this interval. Similarly, here it will be 195 minus, it will be again addition of held component plus censored component. So it will be 184. So during the second interval, at the start of second interval, we were having 195 working components, out of which 100 got held and 1 got censored. So 11 components got out of the system, some because of failure and some because of censoring. So these 11 components have to be subtracted from 195. So 184, these many components will be there available at the start of the third interval. So these can be dragged. So we'll get number of working components at the beginning of every interval. So now during the time interval 0 to 1, there were 200 components available, out of which 5 got failed. So if there are 200 components with you and during that specific time 5 get failed, then we can calculate probability of getting through that particular interval. 195 components out of 200 have gone through that particular interval. So 195 upon 200, that will be probability of surviving through that particular interval. But here there is no censored unit, therefore here there is no problem in defining that way. But suppose if we consider this particular setup, so here 184 components were available, out of which 12 got failed. So 184 minus 12, it comes out to be 172. But it doesn't mean that 172 individuals have gone through that particular interval. It doesn't mean that 172 individual components have survived through that particular interval. Because these 5 were censored. We don't know whether they would have survived that interval or they would have failed during that particular interval. So for this actuarial method works in this way. These 5, instead of considering these 5, half of them will be subtracted from this particular thing and we will get effective sample size. So we'll have another column as effective sample size, and it will be simply the original sample size minus half of the number of censored units. So the number of censored units, if there are say k censored units, we'll assume that roughly every unit was available for half of that interval. So if k units were available for half of the interval, it means that k by 2 components were available for entire interval. So it can be read in that particular way. So this can be dragged. We get effective sample size for every interval. Now for example, suppose if we consider this particular thing 144. So here, even if there were 147 individual components at the start of the interval 5 to 6, but during that specific interval 6 components have been censored. So these 6 components have left the system. So what we will assume is, out of these 6 components, every component was there in the system for half of the interval, that is 5 to 5.5 roughly speaking. So it means that collecting 6 halves will get 3 fulls. That is, this 6 will be divided by 2 and that 3 will be added into 147. Or we can think other way, that remaining 3 will be subtracted from 147. So we'll get 144 as the effective sample size. Now once we get effective sample size and we are having death or failure during that particular interval, based on that we can calculate probability of surviving through that specific interval. That is, suppose a time interval is given and say 20 individuals are entering into that time interval, and out of those 20, 5 got died in that particular interval. So it means that out of 20, only 15 survived. So 15 divided by 20, that will be the probability of surviving through that particular interval. So it is nothing but what is the probability of not surviving through that interval? It will be 5 divided by 20. So 1 minus 5 divided by 20, that will be probability of surviving through that specific interval. So we'll be calculating that probability. It will be denoted by pi, and it will be nothing but 1 minus number of deaths during that interval divided by effective sample size. So out of 200 individuals, 5 got died, and therefore probability of not surviving through that interval will be 5 divided by 200. 1 minus 5 divided by 200 will get probability of surviving through that specific interval. So it will be 0.975. Same thing can be done for all other intervals. So now if we consider any probability, say suppose this probability 0.989291. So what this probability actually denotes is, if you are alive at the start of the interval 7 to 8, what are the chances that you will be alive throughout that interval? What are the chances that at the end of that interval you will be alive? So that probability is given by 0.9291. Now suppose in a particular interval 20 individuals are entering and all those 20 individuals got died during that specific interval. Then what should be the probability of surviving through that interval? Out of 20, no one survived through that interval. It means that probability of survival has to be 0. So for example, suppose here 105 individuals, that is the effective sample size. That means 105 components have entered the interval 8 to 9. At time point 8, there were 105 individuals available. Suppose for example, if we consider during this specific interval 105 components have failed. So if we change 105 here, then probability of surviving through that interval, 105 have entered in that interval and all 105 have been failed during that interval. So probability of surviving through that interval must come out to be 0. So it comes out to be 0. So I will again change it to original value 4. Now suppose 105 individuals are entering in that interval and nobody dies in that specific interval. So if there are 0 deaths in the interval 8 to 9, so whatever number enters in that interval, all those individuals are getting through that interval. So it means that probability of surviving through that interval must be 1. So if I change this to 0, this probability comes out to be 1. So logically we are doing the correct thing. Now these are the conditional probabilities. So 0.9277, it doesn't mean that this is the probability that you will be alive at time point 7. This is just a conditional probability. This is the probability that you will be alive at time point 7 given that you were alive at time point 6. So it is not the unconditional probability of being alive at time point 7. So suppose we want to calculate unconditional probabilities, then we will have another column as S of t, that will be basically it has to be S cap of t, that will be estimate of survival. Now suppose here we want to estimate what is the probability of being alive at time point 1. So since this is the first time interval, 0.97 is the unconditional probability. This is the probability, actually this is the conditional probability, conditional with condition that this is the probability like you have to be alive at time point 1 given that you are alive at time point 0. Since 0 is the origin, by default you are going to be alive at time point 0. So even if it is unconditional probability, it is as good as conditional probability. So this value will appear as it is here. So I will just give the cell address of that value, so it will appear as it is. Now, what is the probability that you will be alive at time point 2, given that you are alive at time point 1? So it will be 0.94. So this is the probability that you are alive at time point 2, given that you are alive at 1. But what is the probability that you were alive at 1? So that probability also has to be considered if we want to remove the condition. So for this, in order to be alive at time point 2, firstly you have to be alive at time point 1, and then conditionally you have to be alive at time point 2. So it will be simply this event firstly has to occur. Sorry. So basically this event should occur. So this probability has to be considered. Once it is given that you are alive at time point 1, then what is the chance that you will be alive at time point 2 also? So this event is not enough. Along with this also has to be happen. That is, conditionally you should be alive at time point 2 with the condition that you are alive at time point 1. So it will be product of these two things. Likewise, if we want this probability that you will be alive at time point 3, then conditional probability that you will be alive at time point 3 with the condition that you were alive at time point 2, this conditional probability will be this much, 0.933. Now if we want to have unconditional probability, that what is the probability that you will be alive at or beyond time point 3? So that probability will be given like this. Basically you have to be alive at time point 2, therefore this particular probability will come into picture. Along with that, it is not enough that you are alive at time point 2. If you are alive at time point 2, you have to go through that 2 to 3 time interval. So this also should happen, therefore we will consider this probability. So now if I drag this, then I will get survival probabilities at time point 1, 2, 3, 4 and so on. So at this particular time point 10, if it is asked that what is the chance that you will survive beyond time 10, then the probability will be 0.55. But suppose in addition it is given that you were alive at time point 9, then what is the chance that you will go beyond 10? Then it will be 0.970. Likewise, these probabilities can be calculated. So this is all about actuarial method of estimating population survival function. Thank you all.